Hello, my name is Rachel Wood. I'd like to thank you for watching this presentation, which is entitled Creating Red, Reproducing Opaque Red Glass from Iron Age Western and Central Europe. First, I would like to thank Dr. Vanessa Muros, Director of the Experimental and Archaeological Sciences Lab at the UCLA Coates Institute of Archaeology. Without her help, I would not be able to conduct this experiment as part of my dissertation, so thank you, Vanessa. Before beginning this talk, I would like to give a brief outline of the presentation. I'll begin with an introduction to opaque red glass, the regions in which it is found, the chronology, and objects associated with the decoration. Then, I'll discuss the goals of this experiment as related to my dissertation research before introducing the type of opaque red glass I'm attempting to reproduce, found at the archaeological site of Montbouffray or Bebracht in France. I'll also address the questions driving this experiment. Next, I'll discuss the 4 experiments conducted as of mid-March, before ending with my tentative conclusions and ideas for future experiments. So what is opaque red glass? In the case of this specific type of opaque red glass, it is a glass colored by metallic copper nanoparticles, as determined by Farge's 2013 publication on the microstructure of opaque red glasses from the archaeological site of Montbouffray, or colored by cuprites. This type of glass first appears circa 450 to 400 BCE, late Iron Age or La Tène period, and is in use until the early 1st century CE, early Roman provincial period, in Western and Central Europe. This area includes countries often termed as producing Celtic art in the Iron Age. Although found in many countries, major locations are Great Britain, France, Germany, Switzerland, Hungary, and Slovakia. Opaque red glass replaces earlier red coral inlays found in copper alloy-based objects from the late Bronze Age and early Iron Age. Objects decorated with this type of glass include helmets, swords, torques, bronze vessels, horse equipment, fibula, and nails and rivets, most likely decorating chariots. I chose to include an experimental component to my dissertation, recreating opaque red glass, in order to understand the practical knowledge necessary for production, including the formula, temperature, time, and firing conditions. My hope is to shed light on the connections between these aspects of production and the object value of opaque red glass to producers and consumers, specifically focusing on the visual qualities inherent in the coloration and opacity of the glass. Ultimately, I plan to compare the glass I create to ancient samples with the help of scanning electron microscopy and energy dispersive X-ray spectroscopy, or SEM-EDS, which will show the metallic copper or cuprite crystals present in the glass and demonstrate how the techniques of glass making affect the composition of the metal in the glass and, ultimately, its color. This specific type of opaque red glass I am reproducing is considered a new formula, introduced after the Roman invasion period around 50 BCE. According to Brune and Pernod's 1992 study of the opaque red glass from Montbouffray, there are 2 formulas found on site: the Montbouffray type, which seems to be introduced at a later time in the 1st century BCE, and the European type, which bears similarity to other opaque red glasses found in continental Europe. There are many similarities between the glass types. Both are soda-lime silica glasses, are colored by metallic copper or cuprite, and have a high lead content of up to 35% lead. There are also major differences between the 2. While the Montbouffray type has 0.5% manganese, the European type is composed of less than 0.1% manganese. There is 0.4% iron in the Montbouffray type, while the European type shows a higher percentage of iron at 2%. Also, the Montbouffray type is unique as its composition includes antimony, while the European type does not. There are 4 main questions for this project. First, what temperature is needed to produce the red color, and does it need to be as high a temperature as other types of glasses? Second, what conditions are needed to create metallic copper nanoparticles versus cuprite for the color? Third, is the color based on the copper colorant source, the temperature of the furnace, the firing atmosphere, the heat treatment used, or a combination of these factors? Finally, since this is a unique recipe, is it made from scratch at Montboufflers, or can a somewhat colorless base ingot be imported from another location, such as the Near East or Egypt, where we know most glasses in the ancient Mediterranean world are produced, and then heated at a low temperature with the addition of copper to produce the opaque red color? Can it then be made at a low firing temperature and done at any local workshop without the need for specialized glassmaking areas? Let's get into the experiments, where the focus will be on the first 3 questions related to temperature, firing conditions, time, and copper colorant source. Our experiments began in late February of this year, and we have yet to create an opaque red glass. 4 experiments have been conducted using the same formula based on the composition of the Montboufflers glass found in Brun and Pernaut's 1992 article. We chose to use malachite as the coloring agent since this is a relatively common mineral. We based the firing program on Brill and Cahill's 1988 publication on opaque red glass from Sardis. In the first experiment, we used a thermoline 1503M muffle furnace, an electric furnace type, to heat the glass at 700 degrees Celsius for 16 to 24 hours. Although directions were followed for the furnace to shut off after 16 hours, it did not, and so the mixture stayed at 700 degrees for 24 hours instead. We used a porcelain crucible covered with a lid in hopes that this would create a reduced environment and cause the mixture to turn red. This firing program did not produce glass, but it did create a fused product with red and white inclusions and some black or blue vitrification in a few places as seen under the microscope. We could not use the same furnace for the second experiment and chose to use a kiln instead. We used the same mixture from experiment 1 and added it to a porcelain crucible with a lid again. The highest temperature cone on hand, a cone 04, which reaches 1046 to 1077 degrees Celsius, was placed in the furnace, and the mixture was left in the furnace for 6 hours. The kiln did not reach 1046 degrees, as the pyrometric witness cone did not bend, but it did reach between 967 and 1000 degrees Celsius. The glass mixture vitrified, though the glass was green and had many air bubbles, so it did not produce a homogeneous glass. The third and fourth experiments were conducted using the same formula as in experiments 1 and 2. We returned to using the thermoline 1503M furnace and fired the mixture at 1100 degrees Celsius this time for a total of 6 hours. We tried 2 different types of crucibles. The crucible in experiment 3 was a high alumina crucible with a lid, while in experiment 4, we attempted to create glass in a graphite crucible with a ceramic lid, as metalworking studies have suggested that using a graphite crucible creates a reducing environment. Experiment 3 produced a homogeneous green-blue glass. This time, the glass did not have as many air bubbles as we saw in experiment number 2, so that was a step forward. Experiment 4 did not create a glassy product. There were no signs of vitrification, and the final product was black in color. There are many challenges to replicate earlier experiments such as Brill and Cahill's due to the lack of details and publications. Also, the specific type of glass has yet to be reproduced as part of a publication, and therefore there is no formula or instructions on how to create the Montboufflers glass. We have to reverse engineer a formula based on the chemical structure from Brun and Pernaut's study. However, we do know that a homogeneous glass structure can be produced at 1100 degrees Celsius for 6 hours, and we will continue to use that firing program until we produce a yellow, orange, or red glass. We also know that a reducing atmosphere cannot be achieved through the addition of a lid or the use of a graphite crucible. Our next steps are to change the formula of the glass, replacing the malachite with leaded bronze shavings for the colorant to see what effect this has on the glass created. This will be used in experiments 5 and 6, which were cut short because of an issue with a new borrowed furnace. The new furnace has an organic material burned on the inside, and 2 hours into the experiment, the organic material caused smoke and fire inside the furnace, which was very exciting, as the furnace was indoors, not great. We had to stop the experiment. However, the mixture was beginning to turn red. I plan to move the furnace outdoors and let this organic material burn in order to see what happens to the glass mixture, as the smoke from the burning material may have unintentionally created a reducing environment. We also plan to create a reducing environment through the use of wood and/or plant ashes placed inside the furnace, and to reach out to the art department on UCLA campus to see if they have a fuel-fired or gas-fired kiln capable of creating a reducing environment. Modifying the atmosphere of the furnace by flooding it with argon, nitrogen, or hydrogen gas should produce a reducing environment and cause the glass to turn red. I'm hoping to find a furnace capable of being flooded with gas somewhere on campus. Here are a list of sources to read if you find yourself interested in opaque red glass. Thank you for your time, and I hope you enjoy the rest of the conference.